Hi, hello everyone. Thank you for joining us on today's um, hands-on session. We apologize for starting a little bit late. So, okay, this is our data science internship sessions. Like today will be fully related to data science, that's neural networks, what you're doing currently on stage D. Okay, without wasting much of our time, the instructor taking us on today's session, I'm just inviting, his name is Ohakim Emeka. He's a junior data scientist at Harmony AI Labs. So I'm just inviting in and we'll start off with what we have for today. Yes.
Okay, good day everyone. Good afternoon. My name is Nemeka Kim. I'm a junior data scientist at Ameya Labs, and I'm here to show you a hands-on session on neural networks in classification and also in computer vision tasks. So let me share my screen. All right, hope my screen is visible. Okay, so for today we'll be if time permits we'll be talking about neural network classification with TensorFlow and also computer vision task with TensorFlow too. So all right, let's go. So a typical architecture of your classification neural network or neural network for classification is basically there's an input layer, there are some hidden layers, and there's an output layer. So what do I mean? What do I mean? So your input layer is the same number of features as you're inputting. Okay, let me explain. So we did a classification task. The last is it the last stage? There was classification with Python, I think. Yeah. So the number of features that you have, like in a given data set, like the age, the sex, the height, the width, that determines the number of the input layer, number of neurons in the input layer. And there are hidden layers too. The hidden layers can be selected as can be as many as you want. There can be one hidden layer, there can be two hidden layers. Don't worry, we'll show what all this means as we go. The number of neurons per hidden layer, then the output layer. The output layer is determined by the kind of task you are running. So basically, if you are doing a binary classification task, that means you want to predict if something, for example, is a cat or a dog, or if this person will buy your product or will not buy your product, or if you want to predict if somebody a customer will leave your company or not. That means that's a binary classification task, and the output layer shape will only be one. But if you have multi-class classification, like predicting if something is actually a dog like this, or a person, or a photo, that means there are three classes. So the number of classes determines the number of neurons in output layer. Then the hidden activation, which we'll see, the output activation, the loss function, and the optimizers. Those are basically the most important things in a neural network for classification task. So let's start. We're going to import TensorFlow as CF. And the version should be 2.8.2. All right. So for this class, for this session, we're going to use a toy data set. We're using a toy data set because it's easy to visualize, and you can easily see what is going on in the exercise or in the lab. You can easily visualize things in the lab. So for this exercise, we're going to use sklearn data set to import like a toy data set, and I'll visualize it for you. So we'll see what this is doing, what is important. So we're going to import sklearn the data set, import make circles, there are 1,000 examples. Then we have the features, because you have the X features and the labels that you're trying to predict. That's the Y vectors. And to visualize this, we're going to use pandas data frame. So I'll import pandas and so we can see that now there are two features and there's one Y label. There's class 1 and there's class 0. So this is a binary classification task, and these are the features. So let's see the number of classes that we have. There are 500 for the class 1 and 500 for the class 2. So now let's plot it and see what we're actually dealing with. So from this, we can see that there are circles, two circles like of different classes. There's a blue and there's a red. So what we want to do, what the neural network wants to do now, is to try and predict, is trying to try and separate the blue from the red. You get, so it's going to like draw a line. We'll see how it is going to draw a line around this in between these circles. So if you now feed it an example data set, an example class is going to predict if it's blue or if it's red. So we now want to do like some analysis of the data sets. Like we want to see the shape, the length, and stuff like that, because it's very, very important for you to see the what the data set you're working with is basically. But since this is a test data set, we just do basic data exploration. So we're going to look at the shape of the data set. So it's 1,000 examples and there are two features basically. There are 1,000 examples, and we are looking at the first example. We can see that on the X, like if you look at this plot, there's an X-axis and there's like a Y-axis. This is XO, X0, the first feature, and the X1 is the second feature. But it's kind of like plotting it for us to see visually what the data we're working with is. Yeah. So it's good to like plot a data set, visualize it, look at it, and know what kind of model you're going to use for this. Basically, in most of your classification tasks, be it in just sklearn or if you're using a neural network. So in this class, we're going to build it like step by step. We're going to see everything step by step, and we'll see how this model is classifying it. So let me start with this. So let me explain the code. So we're setting the seed to 42. This seed means that what I'm doing, you can do it to like the value I get, the same value you get. So this seed helps the reproducibility you get. So if you take this notebook now and try and reproduce it in your own lab, you get almost exactly the same thing I'm getting, because it's kind of like the randomness of it. Yeah. So firstly, we're going to use the sequential API, and this is how you build a simple neural network in TensorFlow. It's very easy. They call it the sequential API. Yeah. So you first import the TensorFlow keras of sequential. Yeah. And in the list, you now put the dense layer. So this is actually where the network or the hidden layer. This is the hidden layer, and this is the output layer. So let me just continue. You will get the hang of it as I go. Now, after you build your model with the layers, the hidden layer and your output layer, you now have to compile the model. Yeah, you compile it with the .compile method. And basically, remember the picture I said, you need your loss function and your optimizer. Yeah, so this loss function optimizer can be anything you want, but because we're working with a binary classification task, we are going to use the binary cross entropy loss. And for this easy case, we are going to use stochastic gradient descent optimizer. And now, after doing this, now the metric, like how can you grade the accuracy of this model during training and validation? So we're going to use the accuracy tag. So now that we've compiled the model, we can now fit the model on the data set that we have, on the data set we have. So we just call, because here we built the model here, we've compiled the model with the necessary parameters, that means the loss, the optimizer, and the metric we want to use for grading. Now it's time for us to fit the model. So those are the three basic steps. You create your model, you compile your model, and you fit your model. So you fit the model on your data set, the X features, the labels, and the number of epochs you want. The epochs is the number of times the the model will try to minimize the loss. You know, the epochs is number of steps it takes to try and minimize the loss. So we'll see that. And the verbose means that we'll see the output. So if I set it to 0, you're not going to see the output. But if I set it to 1, sorry, so if I set it to 1, it's going to print out the output for us. So let me run this. So it's building. Now you see that it's training. Now we can see that there's something wrong with this model, because I told you we're going to build this sequentially for this so that we can easily understand. We are going to notice that the accuracy is just like 50%. So the accuracy is like just hovering around 0.5, 0.49, 0.5. So that means that this model is just 50% accurate. And what is 50% accurate? Like, you can guess. It's just like guessing, basically. So that means this model is not actually working properly for our task right now. We see that it's just if you evaluate on this model, we see that it's just 0.5. It's not improving, it's not getting better. The loss is looking like as if it's still just fluctuating around 0.69, and the accuracy is just 50%. So this model is not good enough. Like, it's just like it's guessing. So now let's talk about how to improve a model, like how to get your performance to get your accuracy, or whatever metrics we're using to grade our model. How can we improve this? That's what it means by improving a model. You see, so there's basically like a lot of ways to do that, but like, let's talk about this one here. The first thing is adding layers. So this is, if you look at this example, this smaller model, you see that there is just like the one layer and the output layer. But in this one, they are like this is the input layer. Then there's 1, 2, and 3 hidden layers, and 1 output layer. And even in the hidden layers, there are now like 100 neurons. So those neurons are those number of circles you see. Like in a neural network, you see a circle, a circle, a circle here. If you visualize it like in picture, you see like this 100 means the number of neurons in just one layer. I hope what I'm saying is getting clear. And you look at the number, another way of doing it, of increasing your model, the accuracy or the performance of the model, is increasing the number of hidden units. And that's what I was talking about. In here, there were just 4 neurons in one hidden layer. But in here, there are 100 neurons, and they increase the layers by 3. You can also change the activation function, which like is kind of pretty advanced. Then changing the optimization function, if we are going to do that. So you see here, they use the Adam optimizer. What we use here was the stochastic gradient descent optimizer. So what makes them different? Well, what this Adam is scientifically, like, people in the field have proven that the Adam optimizer is better than the stochastic gradient descent optimizer. So that's why people in the field use Adam optimizer in most of their cases. Also, another way of improving your model performance is by changing the learning rates, which we'll also cover as we go, and fitting on more data. So the more data you feed to your model, the better the accuracy. We are going to cover in the computer vision task what they call data augmentation. When you have data, but it's not enough, so you have to augment it. And we will talk about that in computer vision task. Is still like when we finish this. So when you increase the number of data that you feed to your model, the accuracy gets better over time. And also increasing the number of epochs. That what we mean by fitting for longer. What if we increase this to like 200 or 300? Even though there are some disadvantages of increasing number of epochs, in some cases, it improves the accuracy. But in this case, it didn't improve. We see that it's just jumbling about 0.49, 0.5. So let's go on so in this case now, let's see. Let us increase the number of layers to 3 layers. Before we just used one layer here, one dense layer and one output layer. But here, let's increase the number of layers and the number of neurons from 1 to 110. Then let's train and see if it will get better. We also see here that it's not looking like as if the model is improving. We see it's still jumping around 0.5, 0.47. So our model is not still increasing. It's not still improving, even though we are increasing the number of layers and increasing the number of neurons. So now, in this case, in most machine learning tasks that you find yourself in, and you see that your model is not improving over time, there's something you need to do. You need to visualize. You need to visualize your data, visualize the distribution, visualize a lot of things. Because when you see something, you understand what is happening in the model and why your model is not improving. Is a very important thing in the field. They call it exploratory data analysis and visualization EDA in the field. So let's try and visualize our data and visualize the output is bringing. So what we're going to do now is we're going to create a function called plot decision boundary. What it will kind of plot is a very complicated function, but it will kind of plot the function, sorry, the data is now going to plot the prediction that the data is making, that the model is making. So let me run through this. If I think I will share the notebook with you, and you push like look through this and see, like, I don't know if most of you understand what it's doing. It's building a mesh grid, and I also put links to where you can understand what this particular function is doing basically. So in your spare time, you look at the function, and it's pretty easy to understand. But let me not like go into that because it's going to take some time if you go into that. So what I'm going to do now, I'm going to plot the decision boundary. So we see that this is what our model is classifying. You can see that this blue there is classifying blue in it, and also classifying red in it. And in this red plot, red side is classifying blue and classifying red in it. So you see that is almost 50, like half of it is just plotting a line, and it's classifying this side to be blue and this side to be red. So we see that there's something wrong with this model. It's not it's not predicting well. It's not predicting the classes well. So, like I said, there's something we're missing. In most of the cases, there's always something you're missing. And in our own case, we're missing the non-linearity. So what's the non-linearity? There are like 3 common ones. I won't like cover all of them, but the most common one, the one you see everywhere, even in TensorFlow documentation, is the ReLU. I don't know if some of you have looked at deep learning, gone through deep learning theory, but if I search through the ReLU activation function, so this is how the ReLU is. And I won't like go down deep into what it does, but it kind of helps our neural network to learn to like classify some examples in one area and classify another example in another area, and kind of combines them basically. But let's go. Let's see what's doing. So what we're going to do is we're going to reduce our number of neurons we're using, because even though we increase number of neurons, it didn't get better. We use 100 here. For here, we're going to use 4, because we feel like it's not the number of neurons that is causing the model to not improve. So it's actually because we don't use an activation. It's very common that you use the ReLU. Everybody uses the ReLU basically. So we're going to use 4 neurons and a ReLU for the first layer, for the first hidden layer, and for the second hidden layer. And for the output layer, we're just leaving it like that. One, because it's a binary calculation task, as we said. And also the optimizer, since I told you that the Adam is the most popular optimizer and the most commonly used optimizer, we're going to use the Adam optimizer, and with the learning rate 0.001. Don't worry, maybe if time permits, we'll get into what this learning rate is. So we're going to train and see what's going to happen. But still yet, our model is still hovering around 0.5 accuracy. So that means we're also missing another thing. If we evaluate and we plot the decision boundary, we can see that, okay, now there are now 2 lines. There are now 2 lines here. There's 1 line here and 1 line here, signified by these 2 activation functions. And so this line and this line is caused by these 2 activation functions here, basically. So what this means is that we are missing something else. So most of the time when you're stuck, you always need to research, check the documentation, read, when you're stuck in any computer vision machine, any task you find yourself in, most of the time when when your model is not improving, it's something that you're not doing right. Maybe in your visualization, your modeling, or something like that. So you need to research and make improvements every time. So the last thing that we didn't put was the sigmoid activation function for the output layer. So what the sigmoid function does, let me see if I can. The sigmoid activation function. So look at it. If I can get a clearer view of it. Yeah. So I hope we can see what this is. So what the sigmoid activation does is it gives you probabilities basically. So now we have 2 classes. The probability that is in the first class, since this is between 0 and 1, probability is always between 0 and 1. The model will predict if the probability of it being in class red, maybe it's going to give it 0.7. So the model will now look at it and say, since it is above the 0.5 threshold, that means this class, or this example is, this example is in class 1. If it's below, that means it's in class 2. So that's what the sigmoid activation does. It basically like classifies it between 2 classes, class A and class D. So it gives probabilities for it, because the probability of it being in class 1 and the probability of it being in class 2, basically. So that's the final piece of our model that's going to make our model better. So let's train. I put variables equals to 0, so we will not see the output until it's done training. So when it's done circling, you should see that the model is better. So let's evaluate. And now we see that, yes, the model is now predicting at 99% accuracy. That is almost like 0.0001% wrong. So it's like it's classifying everything properly. So now let's plot the decision boundary. So we can see now that there's this line that is around this red circle. So now the model can now classify. If you bring in an example class, let's say at 0.01, 0.01 at here, at this middle axis, is going to predict that, okay, that class is the blue class. And if you bring a model at, sorry, an example at minus 1.0 and by minus 1.0, it's going to be here, because if you remember like Cartesian stuff, so it's going to be here, and it's not going to predict that as the red class. So our model now is now able to classify properly that a particular example is in this blue class and is at this red class within 99% accuracy, which is good enough. So one thing I didn't do here was the evaluation, basically. So in any, let me explain, in any machine learning task you find yourself or they will give you your training data. You have data, right? But it's now left for you, because you need to really grade the performance of a model. The neural network is something that can memorize things very well. It can overfit. They call it overfitting. But what it does is that it can remember the examples you get and can kind of cram it. So if you now feed it that training example again, it will give you the accurate answer. But if you give it answer that an example that it was not trained on, it's not going to be able to predict it well. They call it overfitting. So in most machine learning tasks, you have your training data, your validation data, and your test data. The validation data is optional because it's kind of used for if you are going to do hyperparameter tuning, or you are trying to choose the right parameters for your model. Yeah, but mostly you have the training and the test data set. So after training, you now give it fresh example that it has not seen before to see if it will generalize in the real world, basically. Because if you have a model and you've trained it, in the practice, when you deploy the model in production, it's going to get data that it has never seen before, and you want to see how it will perform in for that example, basically. So what we should have done is this: given that we have 1,000 examples, we should have splitted our data set into the train and test. Most of the time, your training data should be more than your test data, basically. So we will split. Our training data will be 800, 80%, and our test data will be 20%. Now we're going to train on the X train and the Y train. So we're going to train on that. You see that the model is improving. With 25 epochs, it got 97% accurate. And now we're now going to evaluate on the test data set, basically, because now we're going to feed it examples that it didn't see in the train data set into like the test data and see its accuracy. So we can see now that our accuracy on the test data set was 100%. So that means that our model did not overfit. Overfitting occurs when your training accuracy is more than your test accuracy. In most cases, your overfit, that means your training, you see some cases your training accuracy will be 1, but your test accuracy will be like 0.8. You see that there's a gap. That means that your what do you call it, your model is overfitting. In the optimal case, your training should not be by far more than your test data set, your test accuracy. And you see that that's what happened here. Our model did not overfit. It's okay. So now we're going to plot the decision boundary of the training data and the test data. And we can see now that even though like we fed in some new data set or some new examples, it's able to classify well that this is in blue and this is the red example. Also, in most cases, you want to plot your loss and your accuracy to visualize better what is happening. So okay, yes. So this is the loss in the next example, we'll see how to use this, like, to know if our data or our model overfitted. So we can see that the loss is reducing and the accuracy is increasing, and it's getting close to the 1% accuracy. So in some cases, you will not want to use accuracy. Accuracy is best when they call it when you have a balanced data set. I won't like go into that completely, but if we scroll up a little, we can see here that our labels, the Y and the X examples, the labels had the same like distribution, they are equal. But imagine in a fraud detection task, when you know that actually fraud is a rare label, like it's a rare case. So you might have, for the people that don't have fraud, you might have 800 examples or 900 or even 950, and your people that in your data, people that can actually compare fraud was like just 50 or 10. You get, so the accuracy will not be the best metric for you to create that model. And there's something there are other ways to evaluate your model. There's precision, there's recall, there's F1 score, and there's AUC ROC. They're like better. There are better ways, better metrics of evaluating your model than just the accuracy. So that will be that for this neural network classification in TensorFlow. And I would like to like go to the next one that we have, which is computer vision with a neural network for computer vision task. So I think we should keep our questions for like this. Well, trying to access.
Mr. Hakim, you're on mute. Please unmute.
Okay, sorry.
Yeah.
Yeah, I forgot. So we're going to go to the next segment, which is convolutional neural networks and computer vision with TensorFlow. So what is actually computer vision? So if, for example, you want to take in an image, computer vision is mostly with visual data. You can see detecting patterns with visual data. So maybe you have an image or images and you want to check if there's actually a cat in this image or a dog in this image, or if, for our case, we're going to detect if something is pizza or not pizza. We're going to check if something is pizza or steak. It's very simple, but it's going to help us. So computer vision is basically deep learning tasks that need visual data, videos, images. There's object detection, where if you keep feeding an image, it can detect. You're going to put the bounding box and it's going to classify if there's a hand or a person or a bike or whatnot. There's segmentation. There are a lot of computer vision tasks. What we're going to do is the image classification. That's like the easiest form of computer vision task. So unlike the simple classification task, there's something different about the computer vision task architecture. So you have your input as images, and now the input layer, yeah, we'll get into that. But what's most different about the computer vision is the introduction of this convolutional layer. They call it the conv 1D, conv 2D, conv 2D. So this is actually the layer that now looks at the image and learns some filters or learns some features or learns some patterns in it. This is the new thing in computer vision task. That is the convolutional layer, and we also have the hidden layer the hidden activation, which is the ReLU. We have the pooling layer. Okay, because of the size, sometimes you have images of 1024 by 1024. There are some really big images, and because of that, the number of features, or the number of features in computer vision tasks can be going to billions. So it's going to take, computer vision tasks take a lot of time because of the number of features, the number of things you need to learn. So this pooling layer is what is very important, because it helps us reduce the number of features by a lot. We will see what it does in the future. And the normal dense layer, the output layer, that is mostly determined by the number of classes. In our case, we're going to predictive is pizza or steak, so it's a binary classification. But in real world, there have been networks that predict like 1,000 classes. Like there's this famous competition, ImageNet, that had over 1,000 classes. Anything you can name: bed, cat, dog, bike, car. So they trained a model that can classify almost 1,000, over 1,000 image, or 1,000 classes in an image, which is really a lot. It was a very huge competition. And we also have the normal output activation, which is the sigmoid or softmax. The sigmoid is used in the binary classification, and the softmax will be used in the multi-class classification, where you have like over 10 classes. So what we're going to do is we're going to import a data set for this. We're going to visualize it and see what we're actually working with here. So let's go. We're going to import. So okay, I need to stop the one I used before. All right. So we're going to download some images from online, from the web. We're going to, because it's going to be a zip file, we're going to unzip it, extract it, and we're going to find it here. Pizza steak. There's a train, and like I told you, you train and you evaluate on a test data set in almost all machine learning tasks. So there's a train and the test. The train has pizza and images of pizza, and we also have steak, which is meat in our country. We call it steak or whatever. And we're now going to create a function that will help us visualize or look at the images. It's going to help us view random images in the folder. So let's plot. So now we can see okay, this is beef steak. This is steak and this is pizza. We can see the shape of the data, 512 by 512 by 3. So I want to in images, there are 3 channels. I did it, I think I skipped it. So you have this image, right? And in every image, there are 3 channels: the red, the green, and the blue. So because these 3 colors combine to form one image. So that's why in almost all computer vision tasks, it's very common that you see something like this. Is like the resolution 3845112, and now this is the number of channels 3. So it's like a 3-dimensional tensor. That's the term they use, a 3-dimensional tensor. So let us preprocess the data, prepare it for a model. So we're going to assign the train and the test directory. So the train is in pizza. I think I've shown you like this. These are the pictures of pizza. These are the pictures of steak. So we're going to train and the test. And now we're going to use many packages in TensorFlow library. So the one we're going to use is the preprocessing package called the image. We're going to import the image data generator class. What this does, it does a lot of things, but for this part, it's just going to help us scale. In all neural net, or mostly all machine learning tasks, you want to scale your data, right? So because these images I can't really plot the shape or the size of data, but the images come in different, let me see, like you can see an image that they have values of they have values from 0 to 255 basically. And since this, what we need to do is that we need to normalize this, because for neural networks to train, it has been studied and it has been found out that you need to normalize, right? You need to reduce it to be values from convert from 0 to 255 to maybe like 0 to 1. Basically, this is what a neural network needs, values from 0 to 1, because it helps them train faster, it helps them get more accuracy as it. So what we're going to do, we're going to use this image data generator class to scale our train and test data. So now this class has a method, flow from directory. TensorFlow has really helped us in computer vision. So if you have your data in folders, you've arranged them in folders, you've put it in train, put it in test, and in that train, there are now like two classes, pizza and steak, right? So what this method does is that it reads through those folders, and it helps us to set the shape we need. It helps us to determine the classes. Look at, since this is a binary class, we're going to tell you that binary classification task, binary sets it to like two classes basically. And it also helps us set the batch size. So what this does is it's going to read through this folder, through the train and test, and get to find all the images under these two classes and prepare it in the right shape for us, right? It's quite easy. And so we see that it found 1,500 images in the train, and it found 500 images in test. Like I said, your train data should be like considerably like 3 times, 2 times, sometimes 10 times, depending on the amount of data you have. It should be more, considerably more than your test data. All right. So since we set it to batch size 32, so these images will come in batches, and that means it's going to be there are going to be like 32 images lined up at once. In neural networks, they do a lot of matrix multiplication and stuff. So we'll call it a 4x4 matrix, but don't worry, we'll see what it does. If we're going to look at the first two examples and the shape, we see that it is 2x224 by 224 by 3. But if you look at when we read it, it was 384 by 512 by 3. So what this method does, it now reshapes it for us. It reshapes the images for us to 224 by 224, which is what most small neural networks use to train training phase, right? So we also like look at the labels, since we are dealing with two classes. 0 is for pizza and 1 is for steak, basically. So what we're going to do is that we're going to create a baseline. In deep learning, machine learning, it's better for you to like start simple, start with a simple model that will train, and you build on that baseline. Basically, in most cases, right? You don't want to rush. You want to build a baseline, see what it does, and build on top of that. So what we're going to do, like I said in the previous class, we used the optimizer Adam. Now in layers, we use a dense layer. In this case, now we're going to use a flattened layer. What this flattened layer does is, because we want to train a classifier. We know we train a classifier, and the classifier cannot take like a 3x3. Don't worry, we'll see what it does. It cannot take this. So we have to flatten it to just something like, let's say 224 times 224 times 1, or by 1, sorry, by 1. So it's going to flatten it out for us, just like a vector, a 224 by 224 by 1 vector, basically. All right, so now this is where we do the actual building of the model. Like in last time, we first create the model, we compile the model, and then we fit the model. Those are the steps we're going to follow here too. So, but in this case, because this is image data, there's a new layer that they add, and they call it the comp2D layer. This layer is what actually does learning in computer vision tasks. It's this number of filters, that means the number of, it's kind of complicated to understand, but I think I will send a link to maybe later to explain that explains what really goes on in this in computer vision, because it's going to take a lot of time to like break down. So this is how you build the model. You have your conv2D. We're stacking like 3 of it, 1, 2, and 3. Then we flatten. Then we predict just one dense layer. Sorry, one output, right? And so we have built the model. We compile it with binary cross entropy and Adam, and with accuracy as a metric. Now we fit the model. What is going to happen is that because we're using, there are 1,500 images, and we're using a 32 batches, it's going to, inside one epoch, we're using 5 epochs. In one epoch, it's going to take 47 steps per epoch. So this is the division it does get. So it's going to take 47 steps. It's going to like try and reduce the, what in reality basically does is try to reduce the loss as far like with the number of epochs. So it's going to try and reduce the, let's fit it first. And we train data 5 epochs, and we're going to use the validation data to plot the true accuracy. So in computer vision, the models take a lot of time to train because they are larger. They are basically very, very large. So we see that the loss is reducing and the accuracy is increasing. So what's in each step, you see that it's taking some time, 28, 36. So in each step, it's trying to reduce this loss and give a very high accuracy. But we can also see, like what I said last time, that our model is clearly overfitting. We can see that the training accuracy is much, much higher than the validation accuracy. So we're going to see that the model is overfitting. Okay, so it's done. So this is a function that is going to help us plot the loss curves. So we see that this thing is reducing. So we can actually plot it on a graph. What is actually happening here? Okay, this is the function. It's going to plot the loss curves for us, and we're going to see it in clear view. So we see now that, look at the training loss is reducing, but the validation loss has started increasing. This is a clear example of overfitting. We see that the training accuracy is increasing, but the validation accuracy is reducing. We see that our model is overfitting in the training data set. So let me now show you what okay, we don't have a max pool here, but this is going to show us the summary of the data set, of the model. So we see 3 conv layers, 1 flatten, and we see that the number of parameters is learning is 477,000. And this is just a small model. And like I said, in other models, we can go to up to, in standard models, we're going to get up to almost 1 billion parameters. So since we are done with that, let me talk about like how to improve your performance. So in like I said in the previous class, the most common way of increasing your accuracy or your performance in computer vision tasks is basically increasing the number of data. Now, there's something they call data augmentation. So because we are working with images, you can like have a pen, an image of a pen. I'm using this as an example. And if you flip it like this, you flip the image horizontally, like if this is how the image is, and you now flip it, right? Now, this is also another image. So what we have done basically is that we have created another image that we can use for training. Like now, we can also flip it upside down, and we also have another image, basically. So that's what data augmentation is basically. We are trying to like just randomly altering the images to create more data. We alter it and we save, we alter it and we save, we alter it and we save. So that's what basically happens in data augmentation. And this is, remember the image data generator that I showed previous time that only rescaled. It does a lot of other things like rotates. Like let me use this biro. You have a picture of a biro and you just rotate it. It's still a picture of a biro and you save it. The sharing is like is kind of sharing. Don't worry. The zoom, like if you have a picture of a cat or a picture of food, any kind of like meat, you can zoom into that picture and it's still a picture of meat, basically. So these parameters, they you don't just tweak them anyhow. You need to know the kind of data you're working with. Like now, if I say that we want to classify a picture of a cat, and we now flip it upside down, that means the head of the cat is down and the legs are up. It doesn't really make sense to flip to do that to your model. Get so there's some alterations that you do that is good, and there are some that you don't do, depending on the kind of data you have. So let's do that. And so this is going to also help us like in the training. Since we have initialized this image data generator, we're now going to use it. So what this does is that as the images are flowing from here, like a piece of this pizza, what it's going to do is now going to apply those transformations for us. TensorFlow is going to help us transform, share, flip, all those things. It's going to do it for us. And now this is an image that I kept for us to see because I think time is going. So like this is an image of pizza normally. This is an image of pizza. But what the augmentor did, or the image data generator did, is that it now flipped it. It flipped it the other way. As it flipped it the other way, it's still an image of pizza basically, and it's now going to feed that to the model, and that's going to increase the number of training data we have by far. So now we're now going to train, and what we're going to do, we're going to introduce the max pool layer. The max pool layer is what I said, is going to reduce the number of pictures we have by half, basically. And we're now going to we're training on the augmented data for 5 epochs, and we're now going to see how the model is going to perform with that. We're going to take more time because we now have more data. Since we have more data, it's going to take more time to train, basically. So but we put it on 5 epochs, it's going to take some minutes. So let's wait and see. So now we see now that the accuracy of the training accuracy or the validation accuracy is more than the training accuracy. So we can see now that because we increase the number of the number of training examples, the model is not overfitting anymore. We can see the validation accuracy is better than the training accuracy. And we can also plot the loss curve. And we can also see it here that if this is the validation accuracy, we know that is neural network we see a lot of haphazard training, but we can also see that the loss is lower than in training and the accuracy is also lower than that. It's going to take some time. Yeah, you see that the accuracy is still lesser than the validation accuracy, which is good, which is a very good thing. Okay, so it's done, and now we can plot the loss curves. Yeah, in this case, it's even smoother. You can even see it clearly now that the validation loss, you see, it's validation accuracy is better than the validation accuracy is better than the training accuracy, which is a very, very good thing in computer vision. And this is because we increase the training data by far. Okay, so in your own case, you can do a lot of things. You can do, we're not going to cover it here. You're going to repeat, you're going to do a lot of experimentation, increase the number of layers, increase the number of epochs, increase the learning rate. And there are other things you can do to improve your model. So now what I'm just going to do now is make a prediction. You have your trained model. Now, how do you make a prediction with it? Right? So, and so these dots is just going to help us get the class names. It's just a very long function that helps us get the class names. I'm doing it because if sorry, I think I was disconnected from. Sorry for that. Yeah, so let me get
No,
back
no
to what I was
problem. You
saying.
can continue. No problem.
Okay, yeah. So now the class, it just helps us get the class names, pizza and steak. And now we're going to get an example data, like something that it has not seen before. Yeah, and we're going to download it from online, and we're going to visualize it. So let's see what the image is. We can see here that it's an image of a stick and it hasn't seen this data before. It hasn't seen it in like any way. It's just a new data, and we want to see how well our model is going to perform with it. And so we're going to look at the shape because it's very, very important that we see the shape. We can see that it's really a really large resolution image, talking about like 4K or so. It's not really up to 4K, but it's close to 4K. And in most cases, you need to perform pre-processing on new data, right? So TensorFlow has functions that helps us with this. So this is going to load and pre-process the image for us. This is a 4000 by 32 by 3000 by 3024 by 3. And what our model takes in is 224. Remember, when we use the I don't want to go back too much. Yeah, the target size is 224 by 224. And we need to do that for data. So we're going to read in the file. It's going to convert that file to a tensor. That's what it does, decode image, and it's now going to resize. We're going to set the image shape to 224. So you're going to make it 224 by 224 of that image, and it's now going to rescale. Those are the important things you need. You first load in your image, you convert it from image to like something that tensor, like to what neural networks understand, which is numbers, and you resize it and you let me run the function, and we're now going to see that it's all between 0 and 1, and it's now 224 by 224 by 3. And this is how we're going to feed the image into the model. One other thing that we need to know is that we need to change the shape of the data, because we are training the data. Let me also show you again. We put this in a batch of 32. So what it was actually, what is feeding going into the network is 32 by 224 by 224 by 3, right? But what is here is just 224 by 224 by 3, right? So now you have to replicate the way your input is, right? And so we're now going to input a new dimension. What this method does is it just inputs a new dimension on the row axis. You can see all this on the TensorFlow documentation, and let me run it. And so I will now predict. So you see, in TensorFlow, networks, your predictions come out in probabilities, really. And so because it comes out in probabilities, you need to now convert from probability to your to your to the stake or pizza, to the list. So that's what we're going to do here. We're now going to convert that to this, basically. I'm really getting faster here because time has really gone, and so this is the last. So it's going to predict and plot. So we said that it was going to is stick, and it's the model predicted that is stick with like an 89%, like it was 89% sure that is stick. That's a summary of it all for this class, basically. So if there are any questions, you can throw them at me.
Okay. Thank you very much. Thank you very much, Joachim, for that interesting session. And I'm guessing they have lots of questions. So you guys know the drill. If you have any question, just signify by using the hand emoji. Raise your hands, then you unmute and ask your question. Because we had like 2 sessions. We did the computer vision, and also the first one was the classification task. Okay, David, you can ask your question.
All right. Thank you very much for this presentation. I really appreciate it. I have a question around that loading of image with channels. Like our normal images normally have 3 channels, like you rightly say, that red, blue, and green. But I also understand that there are some images that normally have like 4 channels. Like probably maybe the 4th one will be near infrared or something. And I don't know if, and I understand that such images carry some information more than the RGB images and all that the model can learn from. Now, I don't know, in reading such images, into TensorFlow or into NumPy, how do we go about loading such images? Because since given the fact that they have more than 3 channels.
Okay, so let me get something. Let me show you something now. So TensorFlow has everything covered. What we used there was conv2D. So there's something they call conv3D. That one is for maybe a like videos now, and that's they call it, what do they call it? They call it 3D rendering. They call it, there are some computer vision tasks that do 3D rendering. So since this is images, that I use conv2D. But if you look at the TensorFlow documentation, there's something they call conv3D, and that will take care of reading higher dimensional videos, also higher dimensional pictures. Yeah, see, this one will take like depth now. That's the newest dimension, and conv3D will take care of that. See, giving a 5D input. So TensorFlow has everything covered with that. Hope that answered your question.
Very well. Thank you very much.
Yeah. Okay, yeah, you can see 7 frames per video. So TensorFlow has that covered too.
Okay.
Yeah.
Okay, thank you for that. Any other questions? I can see in the chats that they enjoyed this session. Okoli is saying awesome class. Kayode is saying awesome modeling. So those are good reviews. So if you have a question, just ask. Raise your hand then. Okay, Isaac, you can ask a question.
Okay, good evening. Thank you, Mr. Joachim, for the great session. Yeah. So I didn't exactly get the last part you talked about where you said we have to resize back to what we initially changed. That's the 32 by 224. Yeah. So I don't know if you could go through that again.
Okay, let me go through that again. Wow. So what I mean is that you know that when you're compiling your model and you were feeding in the input into it, we batched it into 32 like batches. If you remember, So now what your model is expecting is a 4 by 4 tensor. I mean something, okay, let me call it a batch size. That's it. Batch size by 224 by 224 by channel, right? So now it needs something here. So it needs like a value here. So imagine now, so what that method does, imagine if you have a list now, a list like this, 1.2.3. So if you now add a 1 to it, it's now going to put it into another list like this. So like, okay, if I say this thing now, this stuff is 3 by 1, right? Okay, just 3. If I put 3 by 1, sorry, let me put that. If I now put if I put it into another list, it's not going to be 3 by 1 by 1. Do you get? So what the model needs, you have already set it as a parameter, it needs a batch size. And because of that, we need to, and we're using just 1, we just need to extend it. What the method does is just to extend the shape. It just expands the dimension. It doesn't add anything to it. It just expands the dimension by putting it into another list. You can see how many lists are here. 1, 2, 3, and maybe this 4th one. So you get what I mean now? It's just putting another dimension, into another list for you to feed into the model. That's what it does.
Okay, so this new list that's created, did we state what we want to add to it?
Sorry?
The new, like, I get what you said, but like, where did we state what we wanted to add to it?
Yeah, here, look at it. Expand dimension, TF the expand. This is what takes in this previous 224 by 224 by 3 and makes it 1.224 by 224. So this is the method that you.
Okay.
Yeah.
Okay. I still have another question. I think when from the first class on the neural networks, when we started, you at the point you showed us 2 images. One was doing better because it had more neurons, and then we specified more layers, and then the other one was not doing so well because of the opposite. So like when we now went down and like continued with our functions, I realized that I didn't see where we're stating like the input layer. I was just in the hidden layer and the output. So I said I was going to bring it up.
Okay. We don't need to specify that. Like, where is it? Sorry, this stuff is just popping over. Okay, so I think this is what you mean. In this well, actually, we don't need to specify the input layer because we're already using it here. We're fitting it on X train and Y train. Do you get?
Okay.
So we just need to define the hidden layers and the output layer. Basically, that's it. Because we're already putting it, the model already knows, because we're using X train and Y train to fit. It's going to help us with that layer. If you understand what I'm saying.
Yeah, I understand. Then the activation function, must we always use ReLU for the hidden layers? since there are like other activation functions.
Okay, yes, there are other activation functions, but it has been proven that ReLU is faster and
Okay.
I would say more accurate. Yeah, ReLU is faster and more accurate. That's why they use it in almost all hidden layer activations. Yeah.
Okay. Then the epochs, I
Yeah.
saw like what's the like? Can we just choose like very random values when we're like in the initial testing stage, or
Yes,
there's
you
a
can.
there's a better
Yes, you
way of
can.
going about it?
There's
Because
like there's not really better way. It's left to you. They call it hyperparameters. Actually,
yeah,
these are the things
yeah,
that you choose by yourself. These are the things that you have to use your like your mind.
discretion.
After, yes, you plot them. You see a plot. You see whether it's getting better. Then you change it to like maybe reduce it or increase it. It's just left to you. It's left to you as data scientists to do that.
Okay. So, but that will leave you with probably not getting at the end of the day maybe the most optimal value.
Yeah, most times. And there are now something they call, there are some packages that help you. Well, there are some packages that help you with the hyperparameter tuning. They use some kind of optimization stuff to help you optimize. There are some packages, they call it, there's one I know, hyper opt, but they are really complicated. It's really better for you to just do it by yourself. Try out. Yeah.
All right. Thank you so much.
All right. Thank you, Joe.
Okay, thank you very much, Hakim. That was a wonderful explanation. Is there any other question before we wrap it up? Call it today. Okay. So I'm guessing no further question. We all enjoyed this session and understood fully. If you didn't follow up or probably you came late, you can always go to our Hammer YouTube channel. This video is available there. You can watch later and follow through. So thank you very much everyone for joining. Also, as we also know, the interns, the stage D will be wrapping up next week on Tuesday, that's 20th of September. So if you are not done with your quiz or your deliverables or whatnot, you can start wrapping them up now. Okay, thank you, everybody. Thank you, Hakim.
Excuse me.
Okay, you have a question? Yeah.
No. I just wanted to confirm we're expecting the notebooks here to go through.
Yes, so I'll share that with you. No problem.
Okay. All right, thank you.
Okay. All right, so yeah, like I said, thank you very much for this session of Hakim.
All right.
Thank you everyone for joining. When next we have this hands-on coding session, we'll always pass the information on Slack on the announcement channel or your various track channels. So because today's session was basically for data scientists, every other track interns can also benefit too. So the next one we're hosting, I'll also pass the information and you get to know what we'll be doing. So thank you very much everyone for joining. Thank you, Hakim, again. My name is Christian Ajulo Akiono. See you next time for another wonderful session. Have a lovely weekend. Bye for now.